Hi, I'm Dr. Peter Leong, and I'll be bringing you through this topic of distributed and multi-GPU deep learning. So the topics that we'll be going through are the following. We'll first be going through the overview, which is the main content for this section. Then we'll be talking about different kinds of distributed deep learning. First, what we call the data parallel distributed learning. Then we will go on to what we call the model parallel distributed learning, and then followed by distributed learning as implemented using TensorFlow packages, and also we will then go on to additional packages that are used to implement this distributed deep learning, both model parallel as well as data parallel. Although it is more common to find data parallel rather than model parallel, because model parallel is somewhat more complicated than data parallel. So first, the overview of why there's a need to even consider distributed deep learning or multi-GPU deep learning. So here's the background. So for deep learning models, we will face similar issues as what we faced in large-scale or scalable machine learning. The two constraints, the memory constraint and also the computational constraint, the requirement for high computational resources, both of them would appear. So we will actually encounter what was mentioned before, CPU-bound problems, as well as memory-bound problems. So the first aspect is that we need a lot of resources. Why is memory bound? So we need a lot of resources for the large training data sets. In order to store the data set in memory, we may need gigabytes of RAM. But on top of that, um, in deep learning neural networks, the model size would also correspondingly be pretty large uh, because for deep learning, we are making use of what we call weights that are attached to the neurons, and these weights, typically the size of the total, or the total size of the number of weights, is in the order of the same size as the training data set itself, because it has a tremendous learning capacity, but this learning capacity comes at the complexity of the weight architecture. So the more weights you have, the more complicated a pattern you can learn using the deep neural network. But that also means that you need more storage to store the model itself. So unlike some lighter algorithms that do not need, they just store parameters, and you do not need a huge number of parameters to store the model itself. Things like the naive Bayes is quite lightweight because you only need to store parameters related to the distribution, and typically they assume a standard distribution like a Gaussian or a Bernoulli distribution with naive Bayes. So you only need a couple of parameters, okay, to actually so-called find the position of these distributions. But for the neural network, we don't make any assumption about the distribution of the data. In fact, it is highly nonlinear, can approximate any complex relationship. So it is not able to compress the information into a small number of parameters. So every single weight uh, into a neuron in a deep neural network is actually a parameter. So if you have 100 neurons in the first layer, and that's a very small neural network, and you have another 100 in the next layer, is 100 times 100. That's the total number of combinations of weights that you will get just from just these two layers, right? So it's able to learn very complex relationship, but the total number of weights will keep increasing the more layers you have, as well as the wider or the more neurons you have per layer. So if you're trying to learn something quite complex like images that are in their HD quality, which means that you have in the order of one uh, actually it's not 1 megapixel, you will have actually 1,000 by 1,000, so more than a couple of megapixels per image. Then each layer that you have would actually, at least the first few layers will be in the order of 1 million neurons. That's if you're trying to learn from the original image of HD quality itself. So typically we try to reduce the number of pixels necessary so that we don't need to store such a large model. But if you do really want to capture the full quality, that's the kind of size of a neural network that you expect. And hence, this what is this in this statement will come true, right? You need a lot of resource for training data because the image themselves will take a huge amount of memory, and the model that you need in order to learn from those images, because it's also going to be of the same size, or the order of the size will be roughly the same. Therefore, you will also need a lot of resources in memory to also store the model as well. So some essential questions we should ask ourselves, just like what we did in large-scale machine learning. Is it possible to spread out the load, right? Is it possible to distribute the memory that's required to do the training? Okay, for the training set, right? Is it possible to spread the training set over multiple nodes so that we do not need to keep the whole training set in one node? And secondly, is it possible to even spread the model itself over multiple nodes so that we don't need to store the entire model in one node? Secondly, because the training data is large, the training time will also correspondingly be very large. Is there a way for us to actually try to spread out the computation as well, right? Instead of using one single GPU that's very powerful to do all the training, are we able to use multiple GPUs, and hence the name, right? Distributed or multi-GPU training, to speed up the training within a reasonable amount of time. And of course, when we say we want to spread out the training data, we also want to optimize the storage of the model itself. Are we able to not only do the training over multiple nodes, but are we able to spread the model itself over multiple nodes so that each node will only store one portion of the model rather than trying to store the entire model? So this is the background. These are some of the questions that we have. How do we spread the load across multiple nodes, both in terms of memory as well as computational resources? And as mentioned in the topic on scalable machine learning, this kind of problems do emerge, especially as we consider larger and larger data sets and try to build models that can learn adequately from those larger data sets. So in this slide, it shows us the reason why we need to consider larger data sets, right? Because this is actually has been a trend that's been observed in machine learning models, especially deep learning models that we're talking about in this topic. So if you look at the graph here, and it's actually in terms of the number of weights. So in a deep neural network, every single parameter is a weight. Right, so you find that back in the 1950s, we are only talking about 10 to the power of 2, which is like 100 weights in total in the neural network. But as time goes by, you see that the number of weights, they are increasing larger and larger. And if you look actually very carefully, this scale is not really linear, because the first few weights is in the order of 10, then you jump to 100, then to 1000. It's actually a log scale, right? It is because if you try to draw this linearly, it should be much larger than this, because the top level is 10 to the power of 14, which means that it's 10 followed by is a 1 followed by 14 zeros. Okay, so this is a very large number. It's a couple of trillion, right? More than a trillion parameters, whereas down here is only 10 to the power 1, which means just 10. So this is a log scale, and you can see that actually basically the trend is to grow at a log scale, or exponential growth is being observed. So by the time we reach from 1950s to 1970s and early 80s, when the first practical applications of a neural network start emerging. It is not really into the era of deep learning neural networks, but just the classic neural networks with maybe 2 or 3 hidden layers and not too many neurons, right? So you see that already the largest in this era is already 10 to the power 5, about 100,000 neurons. But I guess it will take a huge amount of time to train because the CPU resources available in the 1980s is still in the era of your 386 Intel processor. So it's not really that fast as compared with what we have now. So larger neural networks with 100,000 parameters like this will take some time to train. But you on the lower end of the scale, you do see that some of the lower ends are actually just in the order of hundreds of neurons in this era. And you can see that in different application areas, the growth rate is different. So for example, in games, you need neural networks to control the non-player characters in the game, right? So we can do path finding, etc. It's not a linear. It's a linear growth. If you look at the log scales, and it's actually on the lower end of the size of the parameter weights that it would actually require. Another area like language is where it was growing. Not many applications for neural networks at the beginning, sort of scattered all over the place. There's no clear trend, but actually for the last 5 years or so, it's actually growing at a hyper exponential rate, right? It's like a hockey stick, right? It's actually very, very slow at the beginning, and then suddenly it just zooms up to a very, very large amount. So for natural language processing, which is actually one of the good applications of deep learning neural networks, it has grown tremendously in the last 5 years. So things like GPT-3 from OpenAI, they are in the order of billions of weights or parameters. So when you have this kind of size, right, 10 to the power 12, 10 to the power 10, billions of weights, it's not possible to actually do the training on one single computer anymore. It's just simply too large. It will take too much memory, and also too much computational resources would actually be required to store the model itself. So GPT-3, as you mentioned, is like 10 billion parameters. You can't possibly store 10 billion parameters on just one single machine, right? You take too much RAM space, and to train it, you can't possibly do it on one machine either. So that's actually the state of the art now, right? We are hitting the trillion parameter kind of model, and this growth rate is actually hitting both language as well as other applications like vision as well. So actually vision was driving, or imaging based applications was driving deep learning after year 2000, right? Because it was the best algorithm to do image recognition. But what is driving this lately is more natural language processing. But we have other applications like controlling autonomous robots, etc. This is also growing at an exponential rate. Same with language. Vision applications are still there, but their growth rate has after the initial exponential growth and then increasing, but over the last 5 years we do not observe the same level of increase as what we observe in other applications like games and languages. But what this graph is actually telling you is that the writing is on the wall, right? It has already happened, and we are going to see more and more larger models, and hence this topic is very timely and necessary. As we observe this growth in models, we can no longer do all our training on one single machine for a lot of these newer models that are very, very large. Of course, for the traditional applications that have been tried and tested, especially like image classification, they can be done quite adequately on one single machine. But for the newer models, like the vision transformer that we observe in after 2020, vision transform using transformer architecture for vision rather than CNN, they also have quite a huge jump in the number of parameters needed, because the transformer was actually the architecture that was driving a lot of the newer NLP models. and those things need more memory to store. So looking at it from another parameter, okay, so we can see papers that have been published on various models, as well as the parameter. Again, the parameter size, this is not a linear graph, right? It's actually is a log scale, because the spacing is even, but the number jumps from 10 to the power 1 to 10 to the power 14. And then we have the year on the lower scale, and in this case, for the different domains, the parameter count through history. This graph is actually an expanded version of the earlier one, right? So the earlier one went all the way back from 1950 something all the way to 2021, but we have expanded the last 10 years so that we can see a more clearer trend for deep learning neural networks, because it's only after year 2010 that we actually have a big growth in the number of deep learning neural networks emerging. Prior to 2010, the computational power really wasn't quite adequate to talk about practical applications of deep learning neural networks. Of course, there were papers that were published even in those early days. Okay, but the computational power really came to play after the year 2010, when we had GPU acceleration from NVIDIA, and we also have more funky accelerators, right, using FPGA, etc. So you can see that for the games arena, as mentioned before, is sort of pretty flat, because the control for the path, control for the non-player characters doesn't require you to have too many neurons. In other words, the intelligence level of all these games is not really for entertainment purpose, right? It's not really necessary for it to be too sophisticated. There is still some growth, but it's sort of flattens out and it's on the lower end. For vision, the one that's the green triangles, you can see that actually there is exponential growth, since this is a log scale, even through the era of the evolution of deep learning, but it doesn't really climb at a hyper exponential, so it's still at a steady increase. But last couple of years, because of the emergence of transformer architectures for vision, right, it is also growing a bit at a higher rate now, if they switch over from using convolutional neural networks to transformers. But you can see that the one that's really driving is the language and other applications, right? So traditionally, they follow the same growth path as the vision applications, right? But around 2018, 2020, right, when we start seeing all these newer deep learning architectures like the transformer architecture, the growth rate for NLP, natural language processing, okay, has sort of taken a departure, and actually now it's growing at a hyper exponential. It's even faster than the growth rate for vision applications. Now, if most of the vision applications actually switch over to similar architecture for processing, right, you will probably observe that for vision as well, it will start taking a faster rate of growth in terms of the model size. The parameter count basically gives us the RAM size or the model size that we are building from the data. So this is the model size, right? It's the parameters. It's not even talking about data. So the data itself will be a couple of 100 times or 1,000 times bigger than the model size, because we need a lot of data to actually build a model of this size, the training data. The other application area, of course, would be things like complex reinforcement learning for autonomous vehicles, for robotic control. So, and this also self-attention and all these newer architectures are emerging in this area as well. And you can see that they are also growing, just like the natural language processing, at a hyper exponential growth rate. I would conjecture or guess that one of the reasons driving this is that language and this new other applications, the sequence or the path for the predictions of the models is important. It's not just one single prediction as the output after you get all the input data. Typically for control purposes like robotics, is a sequence of actions or sequence of decisions that need to be made for languages as well, right? So when you talk about language translation, you are not just going to come up with one word as a translation for the input language. You will have multiple words to form a sentence in the new language. So this kind of applications do need a lot more parameters or model size to actually implement. So we come to the last slide. The main idea which I wanted to convey to you for this first initial intro was that the model side, the models, deep learning models, they have been growing at a tremendous rate over the last 10 years, starting from 2010 onwards. Yes, you can observe the scale is actually a log scale. It's not a linear scale. So it's actually growing like 10 times rate over the last years. And of late, the last 2-3 years, for certain areas like natural language processing and reinforcement learning is actually growing at a hyper exponential. This is more than 10 times, a few thousand times a rate. So the need for distributed learning is there to cater for this growth rate, because there's no way that you can actually implement the model as well as the training process itself using just one single machine's resources. It's just too large to do that. So as we go into the subsequent parts, we'll see some of the different approaches that we can use that I mentioned to you earlier at the beginning. So I'll see you in the next set of videos. Thank you.